Hello, this is Michael Sulak, and here's a question from an exam I just gave about a game where you pay $10 and you're going to roll a dice. And if you get a 6, you win $50. If not, you roll again. If you get a 6 the second time, you get your $10 back. The profit from playing this game once has this distribution. And the question that was asked on the last section of this exam was 100 people play the game. What's the approximate probability the person running the game ends up with at least $100 more than when they started? And you can use the central limit theorem to find the mean and standard deviation of the profit from the dealer's perspective. And you get the answer to this as being about 34.7%, but I'm going to show you how to do it a different way, just using a simulation-based approach to come up with this same answer or something that's quite close to this answer. And we're going to do this in R. First thing we want to do is to create a random outcome of this game. So the sample function does that, and I'm going to sample the possible dollar values. I'm realizing that ultimately I'm wondering about what's happening from the dealer's perspective. So from the player's perspective, these are their profits. So from the dealer's perspective, the profits are the opposite. When the player loses $10, the dealer makes $10, etc. So if I ran this, I would get a simulation where these numbers are equally likely, but that's not what we want. We want to have a different probability of each number. So the prob argument lets me do that. And I'm going to assign the value of 10 to have the probability of 25 over 36. And then negative 40 is going to be 6 over 36. And then the 0 is going to be 5 over 36. So if I ran this, I would just get one outcome of this game. What I really want to do is answer what happens when 100 people play the game. If I boost this to 100 and I run this, I'm going to see 100 outcomes of the game and possible profits from the dealer's perspective. And I'm realizing I'm getting an error message because I'm trying to sample more things than I'm sampling from. So when that is the case, there is a replace argument in the sample function, which by default is false, but needs to be set to true when I have a sample of size 100 from just 3 things. So if I ran this, I'm getting 100 simulated outcomes of running this game. What I really want to know is what happened in total, what happened with the combined amount of all of these games. So maybe I'll save this as something called games. And then if I sum these, I'll see what happened in terms of how much money the dealer made in total from 100 games. So on this particular trial, the dealer lost $130 in total. So in order to simulate this probability, we're going to need to do this same procedure many, many times. And so a really nice way to do that is with a for loop. I'm going to write my for loop. I'm going to use I to index, and maybe I'll run it 100,000 times. And so that's the syntax for running something 100,000 times. And now I need curly brackets around everything that I want to do 100,000 times, which I want to run this game. I want to find out what happened from the dealer's perspective. And what I also want to know is, did the dealer end up with $100 more than when they started? What I'm going to do is use a logical expression to see if this sum is more than $100. So right now this is going to either come out to be, well, it's going to be false because currently the sum of games is negative 130. And when I run this, I see that, yes, that's not more than 100. if I ran this loop right now, it will run, but nothing will happen because it checked this 100,000 times, but it doesn't actually do anything with those results unless you could tell it to print it if you wanted, which is not going to be ideal because we're going to get a lot of true or falses. That was 100,000 of them. So what's better to do is we want to save these results as something. And this is the sneaky part with using a for loop. I'm going to save these as what I'm going to call results. But if I run it like this, well, first of all, I had an extra parentheses here. If I run it like this, I don't get an error message, but if I look at results, it's only going to show me what happened in the very last time. It ran this code 100,000 times, but every single time it replaced the value of results with the current simulation. I don't end up with all my 100,000 results. I just end up with the very last one, which is not ideal. So what I'm going to do is save the result of each game, and I can do that by declaring results as an object before the loop. This is important. And then adding indexing to results so that the first time it runs the loop, it'll save the first outcome. The second times it runs the loop, it'll save the second outcome. So what I want to use here is my variable for my loop indexing. And so when this code runs, it'll create a sort of empty object here. We'll get to the for loop. I will be 1. It will create this sample of 100 numbers. It'll sum those numbers and check to see if that sum is more than 100 and save that result in the first position of results because that's what I is. I is 1. Then it gets to these curly braces and now it's going to go back to the starting line of this loop. So now I is 2. So it's going to create another sample of 100 things. Save that in games, and then sum all those 100 things and check to see if that sum is more than 100 and save that in the second position of results. And so it's going to do that 100,000 times and save that as 100,000 positions of results. So now if I looked at results, I'm going to get a very long list of either true or falses. And it doesn't even want to print them all out. There's so many. What I can do now is see what proportion of these 100,000 results are true, because that's going to be the empirical estimate of the probability that the person running the game ends up with at least $100 more than when they started. One way I could do that is I could sum these results, which by itself is just going to tell me how many true values I have. So there were 34,574 true values in there. So then if I divide this by the number of total of simulations, then I'm going to get the proportion, which is 0.34574, which is very close to my theoretical value of 0.3467. And then an even nicer, cleaner way to get that proportion without summing and then dividing by 100,000 is just to take the mean. And when I do that, it's going to treat all the trues as 1s and all the falses as 0s, add up all the 1s, and then divide by the total number of things. And I'll get that same value, that 0.34574. And then I could get even closer if I wanted to by increasing my number of simulations up to 1 million. So generally speaking, the more simulations I run, the closer my empirical estimate will get to this theoretical value that comes from the central limit theorem. So let's see what we get if we run this 1 million times. It's still running. And now I can check the mean, and 3, 4, 6, 5, 7. So we're close to within 10 thousandths. We should have 79s and we only have 57, but we're close to a fairly significant degree of accuracy. And so having this tool is just another way that you can come up with probabilities by empirically simulating them. You don't need to use theory, you just need to use R. And the empirical estimate is equal to the proportion of times that event occurs when done a large number of times. So I hope that was slightly helpful, and this is Michael Sulak. I will see you next time.